For this next part of the lecture, we'll spend some time talking specifically about word recognition and some of the experiments that have been done that have given us some clues as to how this might be possible. When it comes to the study of words, or at least the recognition thereof, we often do a very specific type of experiment, and these experiments are called tachistoscopic presentations. Sorry, it's just a weird word. A tachistoscope is an old device that we used to use before the advent of computers, and it allowed us to show a certain image to a participant for a very, very brief amount of time. This brief amount of time was between 20 and 30 milliseconds, so very short. Please note, just in case, that 1 millisecond is 1,000th of a second, or 1,000 milliseconds make up 1 second. And the way this would work is, just imagine you had a little image attached to an arm that was kind of like a catapult, and it would just flash across the screen, and it wasn't really a screen. It was someone looking through two little peephole type things, as you have those little adventure go places for children. I don't know if they still make those anymore, but you used to have them where there were little two holes for your eyes, and you push you'd stick your eyes on them, and you would just like click a button and it would just show you different scenes. It was kind of like that. I mean, they looked a little bit more complex because they had some lights in them and so on and so forth, but that is basically how it goes. We no longer use a tachistoscope, but we still refer to experiments that present stimuli on screens for very short amounts of time, tachistoscopic presentation experiments. Of course, we do this by controlling how many screen refreshes is an image or item going to be presented on the screen for. Now, there is something else that we do to ensure that this processing is at least limited to this amount of time, and that involves the use of a mask. In this case, a post-stimulus mask, which just means that the mask comes after the stimulus is presented. Some experiments require pre-stimulus masks as well, in which case they will be a mask presented before the onset of the stimulus. And what a mask is something that is oftentimes gibberish presented where the image was immediately after. So if I was to present the word cat and then use a mask, perhaps I would just present some random letters like TWX and then 4 maybe, and I would just put that on the screen immediately where cat was as the time duration for cat runs out. For more physical objects, we oftentimes use random geometric patterns. Now, the reason for this is to ensure that the brain only has a very specific amount of time in which to process the stimuli, so we can truly test how little time it takes for the recognition mechanism to be able to work. And one of the reasons this is thought to be needed is because oftentimes we have a sort of residual piece of information left through our sensory channels when an image is taken away. One common way that you see this in daily life is after images. There is a little bit of a remnant of what you were looking at unless it is taken over by some other type of information. Another place where you see the product of this, even though the actual mechanism is not quite understood yet, is if you happen to be the passenger, let's say in a car, and you're looking over at the car next to you on the freeway, there are certain speeds at which it will seem like the wheels on those cars are not really moving, or in some weird cases, they're moving very slowly backwards. And it was originally thought that this had to do with how quickly our visual system is able to refresh itself, just like a video camera or a computer screen. Some people have thrown or have provided critiques for why that does not explain this phenomena. And some people have said that it has to do with the rivalry between our two eyes seeing slightly different images and a mismatch in the creation because of the high-speed motion of things like a wheel. But nonetheless, it does seem like our visual system is able to process information for a little bit longer than a stimulus is actually presented to us, so long as no other stimulus is presented to take its place. And this is why we use post-stimulus masks, because even if you spent a little bit more time trying to recognize something, you can't actually recognize the thing you were meant to be tested on because now some other piece of information is flowing into your brain. But can people recognize words in 30 milliseconds? And as crazy as this may sound, they actually are able to do so. And they do so at pretty okay rates in a lot of cases. There are, however, some factors that influence how accurately one is able to recognize certain words. The first is frequency, and this refers to how often are certain words presented to us. Now, while this will be unique for every certain person, we generally use a standard metric of how often do those words appear in common literature. So for every, let's say, 1 million words printed, how often did a certain word arise? And we would term something like high frequency as showing up 50 times per every million words. Low frequency, on the other hand, are words that are not shown very often per, let's say, every 1 million words. And again, here you would say something like between 1 and 5 words per million words printed. And of course, you could translate this to online media where it's presented on screens, so on and so forth. And I imagine that if you were to really do enough background examination and studies on frequencies of words, that you would have slightly different lists for completely online media versus printed media, for example. We do find that higher frequency words are recognized more readily and more accurately in such this short time window than low frequency words. So this can be seen in this part of the graph here. So here we have two bars, the first bar representing the recognition rates of high frequency words, and the other bar, which is purple here, represents the low frequency recognition rate. The y-axis here is representing percentage, and this is the percentage of correct recognitions. So if you were to get every single one right, you would have 100% recognition, and if you got none, you would have 0. Here you can see for high frequency words, they're able to recognize approximately 65% of all words presented to them in this unbelievably short time window. Whereas they're able to recognize significantly less words when they are low frequency words, which are somewhere around the order of 35%. And if you spend some time thinking about this, it makes some intuitive sense. There are some strange words that you don't come across often, like let's say quandary, and there are other words that you see all the time, like cat. Well, that's maybe not the best example because one is much shorter than the other, but in most of these experiments, they will control for the fact that the high frequency and low frequency words have approximately the same number of letters and phonemes. Nonetheless, despite my bad example, one can see here and sort of imagine why it is easier to recognize words that one sees a lot because they're just more familiar to us. Now, there is another factor that influences how readily and accurately we are able to recognize words that are presented to us in these very short time frames. And this is the recency of exposure. What this means is, how long has it been since we were last exposed to the word that I'm being asked to recognize? Was the last time I saw this word 10 minutes ago in the same experiment? Was it a day ago when I was reading a science fiction novel? Or was it 5 years ago when I was suffering through a horribly brutal AP English class in high school? Each of those have varying degrees of recency. The closer you are, temporally speaking, to where you're being cued to recognize a certain word, the more likely you are to be able to accurately recognize that word. Here we can see some empirical data to show this. So the blue and the green bars here are the same bars as presented here. You see unprimed or non-recent words for the high frequency are still about 65%, and low frequency unprimed are again around 35%. And this is as we saw over here, where people are able to recognize high frequency words at a higher rate than low frequency words. Now enter priming. Priming is a form in which we manipulate recency, and this can be done in multiple ways. Specifically in this context, we're using something called repetition priming, where likely they showed them the words that were to be primed before they started this experiment, or they showed them multiple times throughout the course of this experiment. Either of those would satisfy repetition priming, which is ultimately we're more likely to recognize or see this item because we have just seen it a little while ago. Here you can see that when high frequency words are primed, our recognition rates of them increases, where it goes almost to 80%, where now we have a bump from a little about 65% all the way up to about 80. So a 15% increase in our rate of recognition. We see an even greater increase in recognition rates for low frequency words when they are primed recently, where we go from about 35% recognition all the way up to about 70-75%, which is a pretty huge jump. That is almost an increase by double in the rate of recognition, which is pretty cool. This data is just showing us that what things we see a lot and when the last time we saw something both influence how easily we are able to recognize objects, in this case words. And remember please that it is important that this is on such a small time frame, because none of this would apply if you could just stare at the word. You could spend all day looking at the word frequency and have no trouble recognizing what it was. In fact, even if you didn't know off the top of your head that this said frequency, you could carefully examine all of the letters and combine it into a word and then recognize the word. That wouldn't apply here because whether it was a high frequency word or low frequency word, we would never be able to see the difference, because if you could spend 10 minutes looking at each word, there would be no difference because you could, at the end of the day, recognize all of those words. Same thing with priming. The priming would have no influence because you would just recognize them by looking at them. Where we see this phenomena happening is only when you have these thresholds at which people are at best able to recognize objects in an unhelped way at about 50% rates. More advanced cognitive science experiments that are done nowadays, where you have much fine-grained or more fine-grained control over computer screens, for example, where you can have computer screens refresh every millisecond, let's say, you can control exactly how long you will present a stimulus. And so what they will do is they will actually calibrate it to participants, whereby you'll have a participant come in and they will do a filler and calibration task before the experiment itself, and they will adjust this time window such that they find the window at which a person only responds at a 50% rate of accuracy, and then they will begin to manipulate it, because then they're able to compare what it would be like to just chance guessing of yes or no, which is pretty wild. Our technology has come quite far in this. What about when it comes to recognizing a single letter presented either by itself or presented embedded within a word? As strange as it is to hear, or even to think about, because it oftentimes defies expectations, we are able to recognize a specific letter more accurately when it is presented within a word than when it is presented by itself. And this phenomena is referred to as the word superiority effect. Now, before we get into talking about it a little bit, this is often tested using what is known as a two-option forced choice paradigm. And what this means is, let's say I want you to see if you can recognize a specific letter. We don't ask if you saw a letter and give you all options of letters to choose from. Rather, what we're likely to do is ask, did you see an E or a K? And perhaps the word that shows up is there, which is going to be one of the examples, and you would be like, yes, I saw an E, or yes, I saw a K, and you would just choose one or the other. The reason for this is that at the end of the day, your just base rate of guessing would be about 50%. Remember how in the previous slide I talked about we can now with modern experiments adjust screen rates and presentation sizes, times, to how much a person is able to recognize and calibrate it down to the 50-50 rate, because that just looks like guessing. And this is why we use this option, because it allows us to have this nice common benchmark to use. This is the same idea as that if you were to go into a multiple choice exam, assuming the answers were evenly distributed across the 4 options, and you just selected C all the way down, that you would probably get about a quarter of the questions correct, just by sheer chance. Theoretically, that's what would happen if you just guessed all the way down, but oftentimes it doesn't quite work that easily. Just a fun fact about me, I have always longed for one day giving a multiple choice exam in which all of the answers will be the same letter. But most times when I tell students this, they freak out, so I probably will never do this. But maybe one day I'll be old and cranky and have tenure, and then I will be able to. But you have not to worry about that because it won't apply to you, because that will be a long way into the future. Okay, anyway. Not all words or letter combinations confer the same benefit when it comes to this word superiority effect. And let us look at some differences here. So imagine you're being asked to recognize the letter E. So you're choosing between E and K, let's say. You will be able to recognize it more accurately, or on average more people will correctly identify the E when dare is presented for, let's say, 30 milliseconds than when just the letter E, is presented for 30 seconds. So people are more often accurate when it is dare than when it is just E. Now, weirdly enough, if you were to present the non-word leif, but notice that it is a word that you can pronounce, it sounds kind of like a word, even though it has no meaning, will also give an advantage over just E. So on average, people will recognize the E more accurately when presented or embedded in leif than when just shown the letter E, which is pretty wild again. But they will recognize the E more often when it is presented embedded in the word dare than when it is presented in the non-word leif. Both, though, do better than just the E by itself. Finally, if you were to present this totally non-word that is difficult to pronounce, which if you wanted to, you would say something maybe like subne. Sorry, just fun pronouncing childish words. Anyway, when you're presented with subne, it gives no advantage in recognition over the letter E. Here you could have the E embedded in the letter combination of S, B, and E, and just have the E by itself, and people will recognize the E at about the same rate. So what's going on here? The way we talk about this is that the degree of well-formedness of these letter combinations is what determines the effect or advantage given by the word superiority effect. And here we would make the assumption that dare is more well-formed than leif, which itself is more well-formed than subne. And, well, what determines well-formedness? And this is based on the regularity of occurrence of word or letter pairings. And we mean regularity in a statistical sense. So what I mean here in this particular example is that the pairings of DA is fairly common, AR is again common, and RE is also quite common. And so these letter pairings are pairings that we see a lot and in larger contexts as well. Now, leif, the reason it sounds kind of like a word other than just being pronounceable is because the letter pairings here are also fairly common pairings. LA is something you see in words quite a bit, AF is another thing you do see in words, and FE is something you see as well. These, however, are a little bit less common on average than dare, or the letter pairings made up in dare. Whereas you can see for subne, or SBNE, the pairings here are quite odd. You will probably very rarely, if ever, see the letter pairing SB or BN. NE, yes, happens, but the first two pairs are very uncommon, and this is what we mean by well-formedness. So if you wanted to be robotic about it, you could go and sort through all words that exist and establish how many times those words are presented, divide all of those into letter pairings, create a graph that had each pairing and how much it occurred corrected by frequency, and then whichever were the tallest bars, whichever ones occurred the most, would be the most statistically regular, and thus a word made of the most tall bars would be the most well-formed word. And a word, if it was even a word, formed by a combination of all of the smallest bars of any kind would then be the least well-formed word. Now, our mistakes are valuable as well. Definitely not what many people are taught in the beginning, because most people are told that mistakes are horrible, horrible things that are just bad, but that's not actually true. We learn from our mistakes, and they're incredibly valuable if you choose to use them as so. They're only useless if you don't learn from your mistakes and keep repeating them over and over. But that's more of a life thing and not a cognitive science thing. So what do we mean by our mistakes are valuable? So first of all, we're again talking about words, right? How we make mistakes in the recognition of words. Now, the data from frequency and priming and word superiority indicate that we're somehow better at recognizing words that we are more familiar with. So when it comes to making mistakes, we also seem to make mistakes in the direction of familiarity. So what does this mean? It means that if I, for 30 milliseconds, was to present you with the word tpum, or TPUM, which is not an actual word, and ask you what word was presented, you might be able to recognize that it was a non-word that was made up of TPUM, but more likely you will actually misread it as trum, which is, I don't believe, an actual word, but it sounds kind of like a word, like Leif from the previous screen, or even misread it as far as drum, which is a sensical sounding word. There are even some reports of similar words being read as far off as trumpet, which is pretty wild, but those are more rare. Now, here you're making a mistake in recognition. Even though you could potentially be reading a real word, it isn't actually a real word, and so if you were accurate, you would recognize that it's not. But the opposite direction of error almost never happens. You will very rarely, if ever, see the word drum presented very, very briefly and think to yourself, I just saw TPUM, tpum, haha. Almost never happens. Even if you were shown trum, you will be more likely to think drum than tpum. So our errors will tend to lead us towards what we are more familiar with, not away from what we are more familiar with. And this is a very interesting pattern in our recognition errors because it gives us clues as to how our recognition systems are themselves functioning.